Now let us apply this result in some triple integral examples where we will write them in terms of iterated spherical coordinates. So, some examples. Okay. The question is, express in iterated spherical coordinates. Of course, when I talk about iterated coordinates in spherical system, we all assume, without repetition at this point, that the iteration theorem is valid for simple regions with respect to spherical, as we did in cylindrical systems and so on. Okay. So we assume we know all those results. Okay. Also for sphericals, I will not repeat the same things over and over again. Of course, where, okay, let S be the sphere, okay, of radius R. Of course, it must be a solid, so with inside part, or more mathematically, with interior part. Okay. So we have then a sphere, okay? And we have a function, of course, which we want to integrate in triples, and this is an R radius solid in space, okay? And we want to write it in iterated form. Well, let us just look at it as follows. Okay, say we want to use rho as the first variable in our iterated formation. So we look at in the positive rho direction. Okay, do we start from a surface and do we end at a surface? Well, we do, of course. The starting surface is always the origin for the rho variable. So we move in all directions, which of course is the positive rho direction. Okay, rho starts from the origin and increases in all directions. Okay, maybe not positive is okay, but increasing is a better word. So rho increases in all directions, so all directions give us the rho direction. Now what we see, well, starting with rho equal to 0, we are already inside S. Okay. And this is a surface. It's a sphere with radius 0, a degenerate surface, but it's a surface. And at the end, we always leave from the surface, the sphere with radius R. And so, clearly, it is simple with respect to rho first. Actually, it's simple with respect to any variable first. As we will in a minute see that, the spherical system changed this into a rectangular box. And so, where you start is not important. So we get, for example, integral over S of f x, y, z dv. Now, all are in x, y, z. Okay. Now, if we write this in spherical system, clearly everything must be expressed in terms of spherical coordinates, which means that x becomes rho sine phi cosine theta, y becomes rho sine phi sine theta, and z becomes rho cosine phi. This is just replacing the variables. Now, as an extra factor, because we use sphericals, we have the Jacobian. Okay, as we remarked, it's already positive, so we don't have to put absolute value. And then we will use rho, and then phi, and then theta. Now, we already figured out that rho changes from the two surfaces. Rho is 0 up to rho is r. In the meantime, in the sphere, measuring from the positive z-axis, the angle phi can go up to pi, of course, and by symmetry, it's directly this one. And finally, theta makes a complete revolution from 0 to 2 pi. Well, in short, the spherical system changes a sphere, centered at the origin, of course, to a rectangular box. So simplifies it immensely. Now, as a second example, let us consider the same question, but here S is, okay, be the part of the sphere. Let me say of the solid sphere, to emphasize that its inside is included, okay, of radius r, lying in the first octant. So the picture now looks like the following. It's a sphere, okay, up to r. But now it lies in the first octant. So it's 1/8 of this sphere. Now, how does this affect the simpleness of the region? It does not. Namely, rho starts from the origin, goes up to the sphere all the time, okay, because it's part of a sphere. So I will not go into details. The integral over S of f dv, in Cartesian, of course, becomes integral of f. As I said, I will not write the details, but we have to write the Jacobian. That's crucial. Now, rho changed from 0 to r as before, because we leave from the sphere eventually. Now, phi starts from the positive z-axis, increases up to the xy plane, which means that the angle spanned is pi over 2. So it starts from 0, but goes to pi over 2. Now, theta starts from the positive x-axis, goes up to the y-axis, which is, again, 0 to pi over 2. So this part of the sphere is also mapped onto a rectangular box in spherical system. So, needless to say, the spherical system is good for spheres and parts of spheres. Okay, now let us go a little bit more complicated. Let S be, okay, be bounded by the paraboloid z is x squared plus y squared, and the plane z is 1. Okay. We already considered this in Cartesian or cylindrical systems. Now, let us look at it again. It's a paraboloid, okay? But it's cut by a plane from the top. So, it is indeed something like this. So this is RS. Now, suppose we want to write with respect to rho first, which is usually common practice, but in some very particular cases, you start with phi or theta, which is not that easy to visualize in general. So let us write this with respect to rho first. Now, when we start from the origin, okay, clearly we are inside the S and we move up to the plane and go out. Okay. But this is not the same all the time. For example, if you make your angle a little bit larger than this one, then you start from here, but you leave from here. Which means that sometimes you leave from the plane at the top, z is 1, but sometimes you leave from the paraboloid. Okay, to see this better, just take a cross section and exaggerate. This is the paraboloid. This is z is 1. Okay, you start from here, you move up to here, or you move up to here. So this is not simple with respect to rho first, which means that we have to make it simple by decomposing it. Now, this cross-section gives us the hint directly, namely, if we divide it into two pieces, exactly in this manner. Okay, which would mean here the same thing like this. Okay? If we divide it this way into two pieces, both pieces, this one and the part around it, you are rotating this, remember, okay, will be both simple with respect to z first, because in this part, which is a cone, when you rotate it, you start from the origin, leave from z equal to 1. These are vertical lines. Okay. Or in the second part, you start from the origin, but you are always below this cone, so you leave from the paraboloid all the time, which means that both of them are simple. So, okay, write S as, okay, a cone union this part is empty. Of course, you rotate it. Okay. Call this S1, call this S2. Both are simple. And so we can express it in our integral. Now for the first one. We want to write it in iterated form. We have f, of course, we have rho square sine phi, the Jacobian. We have the rho. Rho starts from, in S1, the origin and goes up to z equal to 1. So rho starts from 0, goes up to z equal to 1. I will express it a little bit later. Well, in the meantime, phi starts from here, goes up to the edge of the cone, which is to be found. So phi starts from 0, goes up to the cone, and theta makes a complete revolution, so it's from 0 to 2 pi. Now, let us interpret what these things are. Well, z is 1. Means in spherical coordinates, because z is rho cosine phi, that's z, is equal to 1, it means that rho is secant of phi. And what's the cone? Well, the cone is a cone, where actually it's the upper part only. Here, z, that's this height, is 1. Well, it is clearly the intersection of the paraboloid with the horizontal plane z equal to 1. And when z is 1 in the paraboloid, it gives you the unit circle. So, this radius here is also 1, since z is x squared plus y squared, and z is 1. Well, if r is 1 and z is 1, what's the angle between the z-axis and this surface, which is the cone? Okay, this says that, namely, right, r over z, which is the tangent of phi 0, gives you 1. So phi is pi over 4. Now going back, we can now modify the parts we left unattended. Z is 1 means rho is secant phi. So instead of this, I can now write secant phi. And instead of the cone, I can write here, just pi over 4, because that's my phi value. Okay, so this is the first part. Plus, for the second part, for S2, well, in S2, rho starts from, again, 0, but leaves S2 from the paraboloid. We have to work it out. In the meantime, phi, well, phi starts from, in here, it does not start from 0, because when phi is 0, we are on the z-axis, it's not in here, even though you rotate it, because the middle part is empty. So it starts from here, goes up to the paraboloid. But the paraboloid, because it's tangential here, its tangent plane is horizontal at this point, it means that the tangent plane makes, at the end, an angle of 0 with the paraboloid. So it goes up to pi over 2. In short, it starts from pi over 4 and leaves at over 2. However, again in this figure, we have a rotational figure around the z-axis, which means theta makes a complete revolution. So it goes from 0 to 2 pi. So the only missing part in S2 is the paraboloid. Well, the paraboloid, z is x squared plus y squared, of course means rho cosine phi is r squared, Actually, we did this before. It is rho squared sine squared phi, or if you want, maybe we didn't do it, or it means that rho is cosine phi divided by sine squared. Okay. So we must take this and put it. So rho changed from 0 up to cosine phi over sine square phi. Okay. So the paraboloid is not a nice surface if you consider spherical coordinates. Okay. Right. Let me consider calculation of some more triple integrals. This time I will give the functions, and so we will be able to calculate the whole thing up to the last numerical value. That was the second example, so this is the third one. Okay, the question now is to evaluate the triple integral over S of dv over x squared y squared z squared to the power 5 over 2, where S is the set of all points which lie between the two spheres. Okay. Now, what does this mean? Okay, clearly this means that this is being the distance from the origin squared. The distance from the origin squared is between 1 and 2, and so this is the part between the two spheres of radius 1 and 2. So S is in, okay, if you consider it in this form, okay, it is the part between the two spheres. Okay. So this is the annulus between, okay, rho is 1 and rho is 2 spheres. This is S. Well, so of course it calls for a use of spherical coordinate system, obviously. And so using sphericals, okay, we have the iterated formulation. Okay. Here, of course, we have rho squared sine phi divided by rho squared to the power 5 over 2 d rho d phi d theta. Now, as the figure directly suggests, rho changes between the two annuli, so from 1 to 2. And phi, well, we have spheres after all, going up to the very bottom part. So we go the whole distance from 0 to pi, and we have a rotated figure around the z-axis. Okay. Now, what does calculation show us? Well, this is 1 over rho cube okay, and we have sine phi okay, let me put it in the appropriate place. Phi, d theta. Note that because these are not combined together, that is, all variables in the function are just like single variables and they are multiplied, we can evaluate them in any order directly and it won't make any difference. For example, okay, let us look at the phi part. Okay, it changed from 0 to pi. Well, the integral, of course, is minus cosine phi. Okay, and from 0 to pi, it gives us 2. Okay. Theta, well, this is theta. There is no theta anywhere, so it is just pi, 2 pi for theta. This is for phi. This is for theta. Okay. And with rho, we have 1 over rho cubed, which means 1 over rho squared. Okay. When you integrate, you divide by minus 2. And this changes from 1 to 2. Okay. Because of the minus sign, of course, it means that you put 1 first. So you have 1/2 minus 1 over 4. And you multiply this with 4 pi. Okay. So that is equal to pi. Something? No, let me see. Where did I make a mistake? Probably I did it somewhere. Where is that? This is rho to the 5th, so it is 1 over cube. So it is this, that's correct. Right. And we obtain, when we put 1/2, we have 1 over 4. When we put 1, of course, right. We don't get 1/2, we just get 1. Oh, we have this 1/2 here. Sorry. So calculating that, that would be 2 pi, and this would be 1 minus 1 over 4. Okay, so that should be 3 over 4, 6 over 4, so 3/2. Sorry. Well, now let us consider a slightly different example. Okay, the integral is integral over s of x squared y squared z squared dv, where s is given by x, y, z, and x squared plus y squared plus z squared is less than or equal to z this time. Now, what does all this say? If we look at S more carefully, we observe the following. It says that we have x squared, we have y squared, and we have z squared minus z, which simply means z minus 1/2 squared. So we have z squared, okay, we have minus z, and we have 1 over 4. So this should be bounded by 1 over 4. Okay? If you work it out, you will see that, okay, this is a shifted sphere, okay, and the radius should be less than 1/2 all the time. And so we observe that x squared plus y squared plus z minus 1/2 squared equal to 1 over 4 is a shifted sphere. And how is it shifted? Of course, it's shifted in the z direction. The center is at 0, 0, 1/2. And the radius is 1/2. So it is like this. Okay? Radius is 1. So it's this sphere. It's a shifted sphere, but still a sphere. Not too bad. Okay? But we have to be careful with our bounds of the integral. So, first of all, is this a simple region with respect to, say, rho first? Well, rho starts from the origin. We are inside. If we move below the xy plane, we are outside. So we go above xy plane. When we move in the xy, above the xy plane, we go out from the sphere. Well, is there another option? No. So always we go out from the sphere. Well, this says it's a normal solid with respect to rho first. Okay, you have to think here as follows. It doesn't happen, of course, that we go starting from here, something like this. Okay, so we never intersected at 2 points. We start from the origin, so we always leave from this sphere, and so it becomes a simple region with respect to rho first. So we can directly work out what we have. Well, in spherical system, of course, this x squared plus y squared plus z squared is nothing but rho squared. And we have the Jacobian. Okay. And then we have d rho, d phi, d theta. Now, let us go again step by step. Rho starts from 0 up to the sphere. But because it's a shifted sphere, the sphere is not rho equal to constant. We have to be careful there. We have to change this equation into a spherical system. So, since, okay, the sphere is shifted, it is not given by rho is constant. But, okay, let us work it out. Okay, the sphere is actually the equality that we have here. We don't need to complete it to a square. So the sphere is this, x squared, y squared, z squared is equal to z. Now, this is an easier starting point because we already have rho square here, and here we have rho cosine. Okay. So this equality tells me that rho is cosine. So, going back, okay, rho starts from 0, goes up to cosine phi. Okay. Now, how does phi change? Well, it starts from the z-axis, positive z-axis, goes up to pi over 2 because the sphere is tangential to the xy plane. So, it goes all the way up to pi over 2. Well, we have a complete revolution around the z-axis. Theta just makes everything from 0 to 2 pi. Now the calculation part. So I becomes 0 to 2 pi, 0 to pi over 2, Okay. I can even proceed with the calculation. We have rho to the 4th. Integral would be rho to the 5th over 5. And rho changed from 0 to cosine phi. Okay. And after that, we have sine phi, and then we have d pi and d theta. Well, this obviously says that we have 0 to 2 pi, 0 to pi over 2, 1 over 5. Okay. Right. The 5th power of cosine times sine phi times d phi times d theta. But this is not difficult at all. It's because the derivative of cosine is sine phi with a minus sign, okay. It should be, the integral would be cosine 6 phi over 6 with a minus sign, 0 to pi over 2. Of course, we have 1 over 5 here. Okay. Well, at pi over 2, we have 0 anyway. At 0, we have 1. So it is nothing but 1 over 30, okay, times 0 to 2 pi d theta, which happens to be pi over 50. Okay. Well, as a difficult example in these arguments, let us consider the following, where geometric insight will be important. Right. So that was my 4th example. So this would be 51. Okay, we want to find the volume of rho is a 1 minus cosine phi. Now, of course, it's important here what the surface looks like. It looks like a very strange surface. We cannot immediately see what it is. But let us find a parallel between this and the polar system in plane. How? Well, here we don't see any thetas. It means that for all thetas, okay, this is the same curve. In short, okay, since there are no thetas, okay, this is, okay, a curve which is rotated about the z-axis. Is obtained by rotating a curve about the z-axis. Okay. Namely, for any theta, you always get the same curve. And theta constant means you have an intersection with a vertical plane. So all vertical planes give you the same curve. And so when you rotate it, you get the whole figure. Okay. Well, in analogy, with r a 1 minus cosine theta in plane, we get the following. in the xy plane, what is this? Well, if theta is 0, okay, we are in polars now. We are trying to establish an. So when theta is 0, we have 0. When theta increases, okay, from 0 up to pi over 2, okay, this will be 0, so you have a at this point. And when theta increases towards pi, cosine theta will increase towards -1, which means you will have 2a. So you can now visualize. So it follows that we have a cardioid. Okay. Now, this is quite analogous to this one, only, okay, for a fixed theta, rho is the distance from the origin to the point, as in R. In other words, let us fix theta. Okay. Then we have the following. This is theta fixed. And we have theta equal to theta 0 plane. Now in this plane, in this plane, firstly, phi is measured from the z-axis. This is phi. Well, this tells us that in analogy with this example, where theta was measured from the x-axis, okay, in this plane, phi plays the role of theta, but okay, the z-axis plays the role of x-axis. So where we see x here, we should be using z instead of it. So here, okay, the curve theta is theta 0, and rho is a 1 minus cosine phi, okay, is a cardioid, okay, is, okay, like this cardioid, is the same cardioid. R is a 1 minus cosine theta, but theta is replaced with phi, and of course, if you are using phi, you are starting from positive z-axis, so x-axis is replaced by z-axis. In other words, okay, what we get here is exactly the same figure, but instead of x, we have z-axis. Okay, so we have here the following cardioid. Okay. Now the last argument, because there's no theta, you rotate it. So, okay. Now the surface is obtained by rotating this figure, which is like this, about the z-axis. So it is with this part empty. So it very much looks like a true three-dimensional heart. Okay. Now, because it's given in spherical system, we of course use the spherical system. so, okay, volume would be triple integral over S01 dV, but everything in Cartesian. Now in spherical, we have one. Of course, we have the Jacobian. Okay, d rho, d phi, d theta. Now what do we have here? Well, firstly, rho changed from 0, okay, up to the cardioid. Okay, we start from the origin, we move in all directions. That's rho direction. We hit the cardioid, but the cardioid is a 1 minus cosine phi. Now, phi, well, if we look at this cardioid, okay, we see that at this point we have a horizontal tangent, and so here we start with a vertical tangent, so we are immediately inside, and we go up to pi all the way up to down. And theta makes a complete revolution, so we get this in question. Okay. We can calculate this, namely, well, let me calculate that for simplicity. Firstly, theta part, there's no theta in here. Okay, it gives us 2 pi. I can keep that if it does not seem obvious to you. 0 to pi. Now let me integrate the first one. That should be rho cube over 3. So 1/3 of a cube, 1 minus cosine phi cubed, sine phi, d phi, d theta. Okay. Well, that's 0. Clearly, rho cube is 0. Now, in this cube, the derivative of cosine phi is sine phi, or if you want, well, that's okay. So for this integral, you can put, say, u is 1 minus, or just say cosine phi, or 1 minus is better. 1 minus cosine phi, okay? And then du would be sine phi. Phi. So it would be integral of 1/3 a cube u cubed, okay, and du would be cosine phi. Cosine phi is 1 minus u, okay, du. See? No, something is wrong. How do we make it directly? Well, the derivative is this, so that's okay. It's just du. Okay. Right? U cube and du directly. And u changed from at 0, it starts from 0. At pi, it becomes 2. Okay. So, and of course, you have the theta part, but this is calculable. You have a cube over 3, u to the 4th over 4, 2 to the 4th. And finally, okay, let me continue here. It becomes a cube over 3 and 1 over 4, 2 to the 4th. Well, that means 4. And you have 2 pi eventually. So it's 8 over 3, something, something. Okay. Well, the last example in this series will involve a general change of variables in triple integrals, but it will be an obvious one. Okay.